my friends, and welcome to another Cynic video. In this session we're going to be looking at the topic of organic chemistry. Within that we're going to be looking at what crude oil is, hydrocarbons and alkanes. We're going to look at how we can fractionally distill crude oil to separate it into its fractions. We're going to look at how we can crack alkanes to make alkenes. We're looking at what they can do and what alcohols can do, and carboxylic acids and polymers. And just as a reminder, anything that is HT means it's higher tier only, everything else is foundation as well, and if it says CH only, that means chemistry only. It's only in the chemistry course, which is separate sciences. Anything else is in combined science too. So crude oil is a finite resource. It's not renewable, it's found in rocks usually, so we have to drill for it, and it's made from the remains of ancient biomass, usually from plankton that was buried in mud. We dig it out of the ground and it's a mixture. And this mixture is mainly made of hydrocarbons. And hydrocarbons are things that are made of hydrogen and, surprisingly, carbon. They have nothing else. So hydrocarbons do not have any oxygen, they don't have any sodium, anything like that, anything else, just hydrogen and carbon. That's what it's mainly made out of. So it's a mixture, and to make it useful we have to separate it out into its individual components, its fractions, to use them. So most of these hydrocarbons are things called alkanes, and alkanes are hydrocarbons with a generic formula of CnH2n plus 2, which seems a bit bonkers, but you've probably seen it before. The N refers to the number of carbons, so if we have C2, we have 2 carbons, and the number of hydrogens is 2 times by N, which in this case is 2. 2 times 2 is 4, plus 2 gives us 6, so it'd be C2H6, which is actually the formula of ethane. So it looks like this. Now each carbon can have 4 bonds, so it's got a valency of 4, which means it can have 4 of these sticks, and that's really key. So in this case these are all single bonds, they can have 4 individual sticks. For methane it would be 4 bonds coming off of it, just hydrogens. Now the first 4 that you need to know are methane, ethane, propane and butane. The way that I remember this is by the phrase monkeys eat peanut butter, which is a 1 carbon, a 2 carbon, a 3 carbon and then a 4 carbon. It does go on, so you'd end up with 5 carbons, obviously, which is pentane, and 6, which would be hexane, and it goes on from there. But we only need to name the first 4 for alkanes. So ethane, methane, ethane, propane would just be another 3 carbons in a row. Each one has 4 bonds coming off of it. And any of these remaining ones I'd fill in with hydrogens. My hydrogens look a little bit funny and rushed. And butane I don't need to draw because it's just the same again, it's 1 more carbon. Okay, but we need to know here the formula for how many carbons and hydrogens there are, and we need to be able to draw their structure for the first 4. Good. Now there's a key question here as to how can we separate out crude oil into its fractions, because it's a mixture. So it's a mixture that needs to be separated, otherwise it's not as useful. If we can separate them out we can get things like petrol and diesel. Kerosene is a fuel used in planes. We can get heavy fuel oils, and we can get liquefied petroleum gases like propane. And it's really nice, so we can separate them out and they can be therefore useful. If you have all of those things mixed together, they're no use really, because they all have different flammabilities, viscosities, and it just makes them difficult to use. But we can use all of these things to obviously make fuel, but we can also use them to make things like solvents and lubricants and polymers and detergents. Those are the terms that we need to know from the specification. So how do we use fractional distillation? Well, firstly we have to have our crude oil mixture being heated, and the heating causes it to evaporate, and it evaporates the majority of the mixture, so we're heating it beyond its boiling point, which then comes into this fractional distillating column, where we have a region which is very hot, and as we move up through this chamber it gets progressively more cold. And so as they move into the chamber, they basically will rise up, they will travel up through this chamber, and as they get to each section they might reach a point at which they reach a temperature which is below their boiling point. And if they do that, they will condense and then they will flow away from the chamber. So in this first one you'll have some really long chains of carbons, hydrocarbons that basically remain in liquid form, don't actually evaporate. Here in the hot section, they would cool down enough, even though they're warm, they're hot, they'd cool down enough to actually condense, and they'd be tapped off. And the next shorter chains would then do the same, and do the same, and do the same, and we end up getting these different fractions, a group of them which are similar length, which we call petrol, a group which is a similar length, which we call diesel, and so on. Now, the reason that they separate is largely because of the length of their chain. So we tend to have very long chains down here at the bottom of the chamber and very short chains towards the top. When I say chains, I mean length of how many carbons there are. So the little n is very high for long chains and very small for short chains. So we might be talking about propane up here, which might be C4H10, for example. And down in the long chains, we might be talking tens of carbons. But the properties that these chains have are dependent on the length of the chain. So the longer the chain length, this is the key bit that's going to apply to all of these properties, is that the longer the chain length, the longer they are, the stronger the intermolecular forces that are holding them together. So if you imagine there are intermolecular forces between molecules, if these molecules are longer, there are more opportunities for them to form these intermolecular forces, and so therefore the total intermolecular force is greater. And as a result of that, properties like boiling point and viscosity and flammability are affected. So if we get longer chain length, the boiling point will increase. We need to put in more energy to cause it to boil, to cause it to turn into a gas. The viscosity, the longer the chain length, viscosity is how slowly it flows, which is a bit like how thick it is, how gloopy it is. And if we get a longer chain, it increases its viscosity. And the flammability, on the other hand, will decrease. If we have a longer chain, it's more difficult to cause it to catch fire, because to cause it to catch fire, we need to burn every single bit of this chain apart to catch it on fire. It's actually to do with how much it turns into a gas, but the shorter the chain is, the easier that is to happen. So the shorter chains, like up here, are more likely to be used as fuels, especially like kerosene and methane, which is a gas, and propane. They burn very well, whereas the long chains are very difficult to get burning, so they're not very flammable. But if we can cause them to burn, we do something called a combustion reaction. So here we have C3H8, which we can work out the name of because we can do the monkeys eat peanut butter. It is a 3 carbon, so it's 1, 2, 3, 4. So this must be therefore propane. It follows the CnH2n plus 2 law, and so therefore that is propane. So if we burn propane, we're reacting it with oxygen, and if we do complete combustion, we always get a complete breaking of that molecule down using oxygen. So we get completely CO2 and H2O. Now we of course need to balance this, so there are 3 carbons here, so we'll call it 3CO2. And how many hydrogens do we have? We have 8 in total, so we need 4 waters. Does that balance it out? Well, we've got O2 times by 3 gives us 6, plus another 4, that gives us 10 in total. So we don't have enough oxygens here. How do we make that up to 10? We can multiply that by 5, and then that's balanced. So complete combustion is always using enough oxygen to produce carbon dioxide and water. And when you look later in this paper, you'll be looking at how incomplete combustion can sometimes produce carbon monoxide, which is when we don't have enough of the oxygen, and we end up producing carbon monoxide, CO, instead. As we said earlier, these long chains of alkanes are not very useful, so we have them being very long, and they end up having very strong intermolecular forces, and because they're very strong, it makes them difficult to separate, makes them less flammable. You need to put in more energy to turn them into a gas. They're generally not very useful. So what we can do is something called cracking, where we're literally going to break these down into bits. We're going to break them into one alkane and into this one alkane into a shorter alkane and an alkene. So for example here we have a 10 carbon alkane. It's going to break it into an 8 carbon alkane and a 2 carbon alkene. Now an alkene, for this to happen, we're going to take a chain, for example, where we've got whatever on this side, whatever on that side, and we've got our hydrogens here, and it's bonded. we're literally going to crack this down the middle, remove this bond. And by removing this bond, we actually have to do a bit of a rearrangement, and it means that we end up getting at one end an alkene, and at the other end we have to take away a hydrogen from the other molecule, and we end up with a double bonded carbon with hydrogens on the other end. And that double bonded carbon is an alkene. And these alkenes are much more reactive because they've got an opportunity to bond. They've got a spare bond here. It almost held in potential. See, this double stick is a double bond. And this double bond can lead to that carbon reacting with bromine. It can be used to react with other things like water to make alcohols. It can be used to make loads of things. We'll look at them in a little bit. But we can test for them. It's something we do need to know. We can test for alkenes by using bromine water. And when they react with bromine water, which is a brownie colour, it will turn colourless. And that will basically show the positive result of an alkene being present. And these alkenes are also used to make polymers and other chemicals because they're so reactive. Wonderfully simple. Cracking is a process. Generally, we need to have a high temperature to provide lots of energy, and a catalyst to make it faster. Now, for this section, which is chemistry only, we need to be aware of the reactions of alkenes, and later we'll look at alcohols. And let's first look at the structure of an alkene in terms of its formula. So the formula this time is slightly different. It's CnH2n, so we're missing the +2 part. So if we have C6, we then have 2 times by the number of carbons, which gives us 12, C6H12. And to draw them, we need to be able to draw the first 4 alkenes, which you'll notice don't start with methane, or methene this time, because we need to have a double bond between carbons. And if there's only one carbon, which is the case with methane, we can't have an alkene. So we have to do the first 4, which are from 2 carbons up to 5 carbons for pentene. So we draw them with with the first one here with double bond, which is ethene, and then each carbon needs to have a total of 4 bonds coming from it, so we then populate the hydrogens afterwards. So carbon for each one here has 4 bonds, 2 hydrogens on each. For the next one, for propene, again, we've got the rest of the hydrogens drawn in there. This one at this end already has 2 bonds, so we need 2 more bonds coming off of it, which are hydrogens too. Wonderful. Just double checking this carbon in the middle here, it's got 1, 2, 3, 4 bonds coming from it, and the one at the end, 1, 2, 3, 4. Happy days, brilliant. For butene, we again are double checking, we've got a double bond here. For this middle carbon, we have 1, 2, 3, 4 bonds, and this one at the very end, we have 1, 2, so we need another 2 hydrogens coming off of it. I'm drawing these ones diagonally because it's how they should be drawn, but it doesn't really matter at GCSE. And this final one, we'll do exactly the same again. And again, this hydrogen could instead be drawn down here. It doesn't really matter as long as we've got the right number of bonds there. Simple. Now, as we said earlier, these alkenes have really good potential to react with things. With oxygen, nice and simply, they're going to burn. If we have plus oxygen, it's combustion. So as we saw with alkanes, you're going to get the same thing. You're going to get CO2 and water being produced if you completely combust them. For hydrogen, though, if reacting them with hydrogen, because we've got this opportunity, this valency, if we like, if we draw out this alkane, hydrogen, 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 alkene, sorry, not alkane, and then we give it conditions where it can react, we're going to get rid of the double bond. So now it's got a single bond, and we've got an opportunity for an extra thing to bond with each carbon. So if reacting it with hydrogen, we're quite simply going to add a hydrogen here and a hydrogen here. And we've made an alkane. Wunderbar. Simple. It's good. If we get rid of the hydrogens, and then we react it with water, water is in fact made of H plus and OH. H plus and OH minus if you separate it. But if we then add the H plus to one end and the OH to the other end, we get something called an alcohol. In this case, we've made ethanol, which is alcohol you find in alcoholic drinks. Pretty magic. And the final example here is with halogens, and if again we remove these two groups, and a halogen, for example, bromine, Br2, we're going to add at each end bromine, Br, which is why if we had the bromine water, which had a browny kind of colour, and we're reacting with an alkene, the bromine is being absorbed and reacting with, bonding to that alkene, and so therefore is no longer found as bromine as it was before, so it's not going to give it colour anymore. So we get a halogen alkane. We spoke briefly there about alcohols and how they can be produced by reacting an alkene with water, and alcohols have specifically a functional group of OH, and the functional group is the bit that's attached to, or the bit that defines it as a group. So if we look at a final carbon here, whatever was there before, we have this OH on the end, and it is that OH that makes this an alcohol. So all types of alcohol will find this OH on there. So methanol has OH, ethanol has OH, purposely drawn the other way around. It doesn't matter which way round this molecule was drawn, but it typically has to be on the end at GCSE level, and OH there. So we've got methanol, ethanol, propanol, butanol. All of them are alcohols, but they all have different chain lengths. And these can be made, the ethanol for example, can be made by fermentation from sugar using yeast. Epic, legendary, ancient recipe for making alcohol. Ethanol is the one that's being produced by that yeast. We can also use the addition of water to alkenes to do that. So if we had butene and we added water as a reaction, we would get butanol being produced. Reactions with these are wonderfully simple. The reaction with sodium, what it will do is basically produce some hydrogen gas, because what it will actually do is it will remove this hydrogen here from the methanol, and it would then react with, or bond with, the oxygen, and it makes a sodium ethoxide, which is pretty cool. If we burn it in air, complete combustion again, going to get CO2 and H2O. If we add it to water, it's going to quite simply dissolve, and if we react it with an oxidizing agent, we will get a carboxylic acid, which is next on our list to look at, which is where we've turned our OH and added a double bonded oxygen to the carbon instead. So turning it from an alcohol into a carboxylic acid. I should write that in really. It dissolves, it's soluble. However, longer chains tend to be less soluble than shorter chains. Now, if you like pigeons, you like carboxylic acids, because the functional group for carboxylic acids is Crude. Yeah, I know, it's ridiculous, isn't it? Yeah, I hate myself sometimes. Anyway, it looks like this. We've got a double bonded oxygen and a OH group on the carbon. Methanoic acid has one carbon. It still needs 4 bonds, so we've got 1, 2 for the double bond, 1 for the oxygen, and 1 for this hydrogen that's left over. For ethanoic acid, we've got double bonded oxygen again. We've got OH from it. Again, double check the number of bonds. Propanoic acid, same pattern. Butanoic acid, again, double bond oxygen. You get the idea. Now, these have some pretty nice reactions that we can do. First is to note that these are acids. Ethanoic acid is basically vinegar, because it's alcohol that's kind of changed over time. It's actually been oxidized. That's what happens to alcohol, like wine. If you leave wine long enough, it will turn into vinegar. So we get this. And if you react an acid with a carbonate, you should know what you get from paper 1. But if you don't know what you get a salt. You get water and you get CO2. It does dissolve in water. Again, the longer the chain, the less soluble it will become. And it does also react with alcohols in a pretty cool way to make a polymer. Well, actually to make an ester, but we can make polymers from this, where we have our carboxylic acid and a OH group, which is bonded to another carbon with whatever else attached to it, and these two here will bond together where we remove 2 hydrogens and an oxygen to make water, and we make a pretty cool little oxygen bridge, which is an ester bond, which is from something called an ester, which brings us to our next term, polymers. So polymers are long chains of repeating units called monomers. Think monobrow turns into a polybrow, polymer. Polymer has many repeating units called monomers put together. So we have 2 types of polymerization that can take place. The first type is an addition polymerization. We're literally adding different monomers together to make a polymer. So for an example here, we have ethene, and if we have n number of ethenes, we can bond them together in a long chain to make many ethene, called polyethene. And the way that we draw it is by doing this. We've got an elongated bond either side. We've turned our double bond into a single bond. We've got brackets through those bonds here to represent that that's the repeating unit. And then what we can put next to that is n, for we have however many repeats of that subunit from however many we put in. Simple. The one thing to note is that the name of whatever we had to begin with goes in the brackets, so polyethene, because it was ethene here. Simple. Condensation polymerization is slightly different. We're not just adding them together, we're getting something out of it. It's the thing that develops on Windows, which we call condensation, which is water. So here we have 2 monomers with functional groups, 2 functional groups that are bonding together, not just alkenes, which are turning from double bonds into single bonds. So here we have, as an example, an alcohol at each end of the carbon molecule and a carboxylic acid at each end of the carbon molecule. And what we're going to do here is, as we saw in the previous little bit looking at alcohols, we're going to actually react the OH of one group with the OH of another group. And as a result of that, we get a bond removing a hydrogen, and an oxygen to make H2O. We get this bond between an oxygen and a carbon, which is an ester. That's what we're making here. But because these molecules have 2 functional groups, they have the alcohol group at either end, or the carboxylic acid group at either end, they can then make a many-chained molecule. So this box would then be bonded to another alcohol, which would then go on forevermore. And these are really good examples of most biological molecules. So for example, glucose will turn into glycogen or into starch, and that's a condensation polymer. Now we need to know some examples of these polymers. The 2 main ones are amino acids and DNA, and amino acids are found in making up protein. They have 2 different functional groups, so they are therefore going through condensation polymerization. And basically these amino acids will be combined in the same chain but in a slightly different order to make different types of protein. And the order of the amino acids determines the type of protein. So glycine, proline, whatever, valine, cysteine, valine, leucine, they all make a nice long chain to produce an amino acid, a chain of amino acids to make a protein. That protein will fold up into a particular way to make a particular structure. The other molecule is DNA, which is deoxyribonucleic acid. If you say that quickly, you get some points from me. And the other natural polymers that we kind of briefly mention are proteins, which are these ones, and starch and cellulose. But DNA is the molecule that's found in majority of your cells in your body, and it encodes genetic instructions. So it actually codes from organizing amino acids into chains to make proteins. But what it is 2 chains of polymers linked together in a double helix, which is this shape here. Legendary shape, and it's made from 4 types of nucleotides, 4 bases. If you do, well, of course you do biology, but you'll learn about A, T, G, and C, and these are the 4 bases which are arranged in what seems like a random order, but obviously it's been determined over billions of years of evolution. And those 4 bases will code for your genes. Magic. But that's a polymer. It's a condensation polymer. Beautiful, beautiful things. And that, my friends, is the end of this little topic. Hope you've enjoyed, hope it's been useful. If you have any questions or queries or suggestions, do leave a comment, do like and subscribe. Thank you very much.